Okay, welcome back to class. You had a very stressful exam weekend, for which I'm sorry, but at least it's over. There are a few folks that haven't yet taken it, and so I'll decline to answer specific questions about the exam in public, but if you'd like to talk, you're welcome to send me an email. I'll make some time available later this week once everybody's taken the exam for some where you can sign up on a Google Sheet like we've done before for one-on-one time. I'll also post videos that explain each one of the questions, and I'll make it so you can go back in and see the items missed and what your responses were and so on. Just for your information, the average score was around 73%. That's after I started assigning partial credit for some of the questions. And the median score was around 79%, which is really quite good on this exam 3 of the semester, which historically is one of the more difficult exams in 351. So overall, I congratulate you. I'm proud of how well things have gone for you. I understand that for some of you, it may not have gone as well as you wanted, and so we can talk about that and talk about some improvements that can be made. But it's time to start preparing for the next exam. So Chapter 12 is kind of interesting because it's about a different kind of chemistry than we've done so far. Oh, I'm sorry, I'm missing some of the questions that are coming in on the chat. Why did some people score increase and others didn't? Because I play favorites and I gave more points to the people I like more. No, actually that's not what happened. What happened is there were a number of questions that had multiple response and were select all that apply, and I originally made it so you had to get all of the right answers and none of the incorrect answers to get credit. And that was to avoid a situation where someone could select all of the answers and get all of the credit while knowing nothing. After the fact, knowing that that would stress you out, I this morning went in and made it so you got credit for the correct answers. Right now, I haven't put in so far any penalty for incorrect answers. I figured that you all deserved a break. But for those of you who have yet to take the exam, if I see anybody selecting all the answers just to get all the points, I will be most displeased. Okay, let's see. Is the final going to be all of this new stuff in addition to being comprehensive? Yes. The final will be comprehensive. It'll cover stuff from the beginning of class. It will necessarily emphasize stuff that we're going to do now because there's going to be some new subjects. But yeah, it will be comprehensive. Are we not doing chapter 15 today? No, we're going to do chapter 12, which we didn't get to. And we'll try to spend just a couple days on chapter 12, and then we'll move on from there. So we're a little bit behind. Are we preparing for the final, or do we have another exam? The final is the only other exam, 250 points. And yeah, okay. I think that's all of the questions. All right. So oxidation and reduction. What do we mean by that, and how is that different from what you've done so far? Organic chemists tend to think about molecules as in a sort of hierarchy, and since we live in the Benson building, maybe we'll consider 4 different floors. You don't live in the Benson building, but I do. I don't sleep there, though. But I could, because there's a couch in my office. Though it's a little small to sleep in, I guess. But I do have a stuffed animal Chewbacca that I could snuggle, so there would at least be that. On the 4th floor, you have functional groups like carboxylic acids. These are functional groups that have a carbon with 3 bonds to a heteroatom. Notice that back when we were learning about nomenclature, all of these were sort of in the top of our priority list. And there are others that I guess I'm missing, esters and thioesters. but you're looking at sort of 3 bonds between carbon and a heteroatom, where a heteroatom is something other than hydrogen or carbon. So that's sort of the 4th floor. And then on the 3rd floor, you have things that have 2 bonds with a heteroatom, like aldehydes and ketones. There are also equivalents of aldehydes and ketones. These are called hydrates, where instead of a carbon-oxygen sigma and pi bonds, you just have 2 carbon-oxygen sigma bonds on the same carbon. The enol is also at this oxidation state, and there are some other molecules that occupy this oxidation state and are sort of interconvertible. Within each floor, there are reactions that allow you to convert one of these molecules into another. I'm not sure what kind of arrows I want to use. I don't want to put equilibrium arrows between each of these structures to indicate that they're actually in equilibrium with each other. But going from one side to the other here, we call that functional group interconversion. And a lot of times, those kinds of reactions are pretty straightforward, don't require a lot of effort or expensive reagents. Similarly here, there's interchange among these is also called functional group interconversion, except I can't write and talk at the same time. And you've seen at the end of chapter 11, showed you how you could turn a turn a alkyne into an enol, and then that enol would rapidly isomerize into a ketone. And so it's pretty easy to interconvert among those. So that's our 3rd floor. But notice that going up a floor requires addition of a carbon-oxygen bond in place of a carbon-hydrogen bond. And that transformation is a little bit more difficult. On the 2nd floor, you've got functional groups with 1 bond to a heteroatom. And again, these are readily interconvertible via reactions that you know. Substitution and elimination reactions allow conversion in between alcohols and alkyl halides and tosylates. And then sort of on the ground floor, we have hydrocarbons. And I just mean saturated hydrocarbons. Like ethane as an example. Okay? So if we look at what changes as we go from the 1st floor up to the 4th floor, why are we not moving here? I wanted to shrink it a little bit. As we go up the tower, we are increasing the number of carbon oxygen or carbon heteroatom bonds. And we are also decreasing at the same time the number of carbon hydrogen bonds. And we're going to define that as oxidation. Now, in general chemistry, oxidation is loss of electrons, reduction is adding electrons. With respect to carbon, when you increase the number of carbon heteroatom bonds, we're going to pretend like the electrons in that carbon-oxygen bond belong to the oxygen formally instead of the carbon. And so the carbon has lost electrons. Now, it's still a covalent bond. It's still sharing them, but we're going to pretend like those electrons belong to the oxygen. So the more carbon-oxygen bonds a molecule has, the fewer electrons carbon has. You guys ever hear those annoying commercials on the radio where the sort of I don't know, self-important child reminds people when to use fewer and less in the appropriate contexts, or farther versus further? No? Okay, well, look them up. I know there's a grammatically correct way to use fewer versus less, but on principle, I refuse to know. All right, so similarly, reduction involves increasing the number of carbon-hydrogen bonds or decreasing the number of carbon-oxygen or carbon heteroatom bonds. Oxidation and reduction. I should point out that many of the molecules in our chemical feedstocks tend to be on the first two floors. So the fossil fuels are all in the sort of, in many cases, saturated hydrocarbon level. And there are some that have double bonds in them. But the molecules that are useful for a lot of purposes tend to be on the upper floors. And so we have to do a lot of oxidation to make interesting molecules in organic chemistry. I suppose that there's a fourth floor, well, there's a fifth floor, except it's just outside, and that's the fully oxidized form of carbon, which is CO2. And getting from the ground floor all the way up to CO2 is very easy. It's called combustion. And our ancestors figured that out quite a long time ago, and we've been using it. And then over the past 150 years, we've been pumping CO2 into the atmosphere like crazy. And that's having consequences that we and our children and our children's children are going to have to deal with. I'm not an environmental scientist, and this is not a environmental science lecture. But I hope at BYU you are learning to trust and believe good science, just like you trust and believe good doctrine, and I'm hopeful that you won't be persuaded by, we'll call them climate change deniers. Anyway, am I allowed to say something like that? I guess it doesn't matter because it's now recorded and everybody can see it. So, dang. All right. Now, once you've gotten up to CO2, it's actually quite tricky to go back down into the building. How do we take carbon dioxide and reduce it to something that's not a greenhouse gas and to something that's useful? Well, you can plant a tree because plants have this process figured out. There's an enzyme that's called, I think, rubisco. I forget, it's like ribulose bisphosphate something, and it's the most abundant enzyme on planet Earth. And it is the reason plants can fix carbon dioxide into a more reduced form, in the form of a carbohydrate, which can then be used for other things. But in terms of really good industrial processes that do this, we don't have any yet. And so that's an important area of current research. I'll point out that the solution to the nitrogen has a similar problem. The forms of nitrogen that are useful in biology are reduced relative to nitrogen gas. And it was early on, I think in the late 1800s, early 1900s, that this problem was solved via a process called the Haber-Bosch process, which allowed nitrogen fixation to making fertilizer, and that's why we can have 8 billion people on the planet. So you never know when something important is going to be discovered, and there are people working on the carbon problem currently. But we're going to focus our efforts in the class on some simpler sort of issues. The interconversion among functional groups on the on the fourth floor is going to be an item having to do with 352. And most of the stuff on the third floor, there's going to be a little bit of 351 stuff, but most of it's going to be 352. We've already done interconversion of functional groups on the second floor. Getting from the first floor to the second is difficult. We're going to learn how to do this in, I think, chapter 15, which is about something called radical chemistry. And we're going to learn in the next couple of days how to get from alcohols, say, to aldehydes and ketones. And we'll learn how to get from aldehydes to carboxylic acids. We're also going to learn in 351 how to take alkenes down to alkanes, and we'll do the same for alkynes. But we're not really going to deal with going from aldehydes and ketones to alcohols. That's going to be a 352 thing. And similarly for reducing molecules on the fourth floor down to smaller things, that'll be a 352 thing. So that may look sort of complicated, but I just wanted you to get an overview of where we are and what kinds of reactions that we'll be doing. So in chapter 12, these are sort of the areas that we're going to be focusing on. And I guess we'll also be, never mind. All right. Any questions so far? No, you just wish I would stop. Okay, but they're paying me to teach you till the end of the semester, so you just as well get your money's worth. All right, so oxidation reactions you already know. Notice you already know a reaction that takes you from an alkene up to something on the third floor, the vicinal dibromide, right? This is the bromination reaction. And you also know a reaction that uses the closely related cousin of the bromination reaction to give you a halohydrin, which you can then convert using a strong base into an epoxide. So that's a little bit of oxidation chemistry you already know. One of the key features of molecules that are able to do oxidation chemistry is the presence of weak heteroatom sigma bonds. Sometimes these are between oxygen and oxygen. Sometimes they're between oxygen and a halide, as is the case in bleach. Other times they're between two halides. There are also some oxidation agents that have metal oxygen bonds. And so this is the kind of thing that we will be using to do oxidation chemistry. So let's get started on a few new reactions. And I'm going to introduce first a way to get from an olefin to an epoxide in a single step. And that is to use the reagent MCPBA. Reagent alphabet soup. Well, fortunately, since the exams are open book, there's no need to memorize things, though you should definitely be familiar with. What does MCPBA stand for? It stands for this molecule. Do I care that you know what the acronym, where the acronym comes from? Not particularly. Meta M describes the relationship between the carboxylic acid group and the chloro group on the benzene ring. They are 1, 2, 3 atoms away from each other. So that's the meta substitution of the aromatic ring. Meta-chloro, there's a oxygen-oxygen bond there. Meta-chloro peroxybenzoic acid. Peroxy is for molecules that have oxygen-oxygen sigma bonds. All right, so how does this work to take an olefin and turn it into the epoxide in a single step? The mechanism for this reaction is known, and it's a single concerted step, and it looks pretty much like what you've learned for bromination of olefins. So there will be a few other arrows, but the most important ones you can understand just based on what we've done before for the bromination reaction. Okay, so it's electrophile here and nucleophile here. The carbon-carbon pi bond is the HOMO of the nucleophile, so that's what's going to do the attacking. The oxygen-oxygen sigma star is going to be the weak part that the nucleophile is going to attack. So we will attack that sigma star, and that's going to break the oxygen-oxygen sigma bond. Okay, I'm not going to show that process happening just yet, or rather we can pretend it is. At the same time, just as we dealt with in chapter 10, when you involve pi electrons to attack a nucleophile, you've got to decide. You've got two atoms that were involved in that pi bond. One of them gets the new sigma bond, and the other would get a positive charge. Only just like with bromine, as the positive charge starts to build up on the other carbon, lone pairs on the oxygen attack the other carbon to make a second sigma bond. Okay? So that's the key point in how we're going to make two new sigma bonds with the oxygen. Just as with bromination, I will draw the bromination mechanism so you can see the analogy. Pi bonds attack the bromine sigma star, the bond breaks, and other electrons, lone pair on the bromine, attack the other carbon. So that should look familiar. Now, notice that the oxygen in the epoxide doesn't have a proton on it any longer, but the oxygen in the MCPBA does still have a proton. So what I'm going to do next is adjust the arrows to take care of that without doing a second step. Now, to understand this, think about what would happen if we just stopped here and the electrons went on this oxygen. That would be a carboxylic acid conjugate base, and the negative charge would be delocalized between these two oxygens, right? So actually, it's no stretch to, instead of showing the electrons going onto this oxygen, it's equivalent in terms of resonance to simply show this happening. That is, these electrons, instead of going on the oxygen, go to form a pi bond, and then these electrons go out on that other oxygen. That's just a resonance structure of what we would have otherwise drawn. Now here's the kicker. At the same time as that's going on and negative charge is building up on this oxygen, that oxygen just reaches over and removes the proton. It's a 5-membered ring, transition state, the bond angles all work out, and this allows you to get to the final epoxide product and the carboxylic acid byproduct all in a single step. Okay, so you should be able to draw that mechanism. That being said, I mean, how could I ask a useful mechanism and a fun, or how could I ask a mechanism question about this on an exam that wouldn't be just about can you look stuff up, right? It's a single step and all the electrons are going on there. So I know that students in the past have stressed out about this. You've now got it in your notes, so I think you should be able to answer any questions that I might ask on it, though as I said, it'd be kind of all I would be testing with that question would be, can you look stuff up? Which hopefully now that you have Google, you can look stuff up and you've got it. All right, questions so far about epoxidation? Okay, good. So that's your new fast way to make an epoxide. There are lots of other reagents that do this. Now, notice that once we have the epoxide, we can do lots of things to it. And one of the things that your text points out that you can do with the epoxide, once you've got it, is to react it with some nucleophile. So suppose you reacted it with OH minus in water. That would open up the epoxide to form a diol. But notice that in going from the epoxide to the diol, you have not increased the number of carbon-oxygen bonds. You had 2 in the epoxide, you have 2 in the diol. Those are at the same oxidation state. So opening up the epoxide is an example of functional group interconversion. All right. Now, in chemistry, we like to have multiple ways of doing the same thing. And so the strategy of making the epoxide and then opening up to get a diol, opening up with hydroxide to get a diol, is complementary to another strategy that gives you the diol directly. So, and there are a few actual reactions that fall under this category, though we're only going to learn one. We can call this direct dihydroxylation. So here's an alkene, and the reagent of choice is osmium tetroxide. So that's, if you count electrons, that's actually osmium at the +8 oxidation state, so it's pretty high up there. You would draw this with osmium bonded to 4 oxygens. Osmium's obviously is a transition metal, and it has its fine being hypervalent, multiple bonds to oxygen. And in the second step, this is involved, there's a reagent used. I'm not sure why it's this particular reagent, and your book never explains it. But I'll show you what it does in a second. That will generate the diol as a product. Now, the first step of the reaction generates an intermediate that I don't require you to know. I don't require you to know the mechanism of this reaction. This intermediate is called, osmolate ester. You don't need to know that, but now it's instead of being at the +8 oxidation state, it's only at the +6. And so that's what happens after the first reaction. And then the second reaction involves hydrolyzing the osmolate ester. Once you get here, the oxidation process is done. You're just going to replace these osmium oxygen bonds with osmium oxygen bonds from water and liberate the diol. Again, mechanism for either of these, I don't require you to know. Question? No? All right. So there's something else to learn here about these 2 different methods of dihydroxylation, direct and indirect. By the way, I watch my kids playing soccer, and I don't really understand the difference between direct kick and indirect kick and when they're supposed to happen, other than the direct kick, you don't kick directly at the goal, you kick at somebody standing in front of the goal. Is the goal to hit them in the face or something like that? It's okay, I don't need to know the rules to support my children. But anyway. Dang, I had a bad dad moment, though, once, because a couple of months ago, Adam was playing indoor soccer. And sports are really not my jam, I mean, as you can tell. But Adam was at this game, and I'm watching him, and he tells me that every time he looks over to see if I'm watching, I was actually staring at my phone. And I told him I was watching him plenty of the time, but he was right. I was also looking at my phone. So I don't know what parents used to do when they didn't have phones, but were still going to sports games of various kinds. Maybe they cheered for their children. I don't know. Now the parents that are not now the parents that are not looking at their phones are actually yelling from the sidelines, coaching their children on every single thing that they should do. Get the ball. Oh, really? Is that what I should do? Thank you for telling me that, because I didn't know that I should get the ball. Or hustle. Really, I should run. Okay, that will make things better if I just run more. It's all you. Go get it. Go get it. Get the ball, Nash. Get the ball. Poor Nash. Oh, and now, yeah, thank you. Direct free kick can be a shot at the goal, while indirect free kick means someone else has to touch the ball before a shot can be taken. Ergo, hit somebody in the face and then have it go into the goal. Okay. So I've been easily derailed. There's actually a difference in the stereochemical outcome of these two reactions. Oh, Hiram, yeah.
Sorry.
That's okay.
For the direct, if the alkene is not symmetrical, what would we expect to occur?
If the alkene is not symmetrical, well, for the direct dihydroxylation, both carbons get an oxygen, so there's no regioselectivity issues. But there are stereochemical issues. So, I'm just liking these. Okay, I just have to read you some of the chat. My mom. Go, get the ball. Me, it's not in my area. Somebody else, my mom. Go, get the ball. Mom, I'm wrestling. I'm on D and it's in front of the other goal. It's not my job. Yeah, anyway. Parents are great. When you grow up, try not to be helicopter parents. Is that still a thing? Do you guys know what that means? Yeah, okay. All right. That's what we're trying to do as Nathan finishes his senior year. He's already got into BYU and USU, and so now he's like, I can do whatever I want. I just have to graduate. I don't have to get good grades, and we're trying to let him drive that train to its intended destination while hoping that he doesn't actually blow it up. So we'll see how that goes. All right, stereochemical consequences. If you take this olefin and you use MCPBA, you're going to get the epoxide as you expect, and then when you open it up with hydroxide and water, you're going to get the trans diol with its enantiomer, which I'm not going to draw. Because of this, sorry about the terrible penmanship, your text calls this two-step reaction series anti-dihydroxylation. You can call it that if you want to, that's fine. If you call it that, I'm afraid it goes in a different drawer in your mind, and then you see a drawer entitled Anti-Dihydroxylation, you're wondering what the heck is that. It's not any more complicated than opening of an epoxide, which you already know. But I think your text highlights that at this point to demonstrate that in contrast to epoxide opening, dihydroxylation via osmium tetroxide happens on the same side of the double bond. And so you'll get the different diastereomer from the process. You'll get Syn Dihydroxylation. The reason it's Syn Dihydroxylation is because this step, which I didn't tell you about mechanistically, happens in a concerted fashion. The osmium tetroxide sits down on the pi bond. I mean, if you wanted to see the arrows pushed, you could, but basically you form both of these new oxygen-carbon bonds at the same time, and it's only a 5-member ring, so there's no way to do it in a anti-way. Okay? So you've got 2 different ways with 2 different stereochemical outcomes. This now gives me another opportunity to test your stereochemical skills by asking, whoops, how do you make this compound? And can you get there from either the cis or the trans alkenes? Someone asks on the chat, is the anti-dihydroxylation reaction in your study guide? I'm not sure it's called that in the study guide. Frankly, it's a chapter 9 or 10 reaction, opening of epoxides, so it's not new. Would it be possible to have the down arrangement of the Syn diol? Yes. This is a meso compound, so having both of those wedges be dashes would be just exactly the same thing. Okay, so what reagent would I use if I were starting from the cis alkene and wanted to end up with this particular 2,3-butane diol? You're going to use the osmium tetroxide reagent because that's syn addition across the cis double bond. So yeah, that would give you the right stereochemistry. And in contrast, if I wanted to do this with, starting with the transalkene, I could use MCPBA. That would give me the trans epoxide, which I could then open up with hydroxide and water. That's going to give me, and it still happens via backside attack, but then if I rotate around this bond by 180 degrees, lo and behold, it's my meso 2,3-butane diol. So now you got a couple of different methods to accomplish the same thing, but there's stereochemical issues there. And I love to write questions that require you to follow stereochemical issues through to a product and think about the various options that are available. I've definitely written questions before where I had a starting material and a product and you had to choose between these 2 different methods among other bogus responses for what the right answer would be. And so mastering that stereochemical issue is important. All right, other questions? Okay. So let's now oxidize some alcohols up to aldehydes and ketones. I'm going to introduce a new reagent. And the reagent is pyridinium chlorochromate. Easy for us to say. We will abbreviate it like we do with so much else. PCC, which is not as fun as visiting Hawaii, but at least it could make us wish we were doing that. Let's see. So here is an alcohol. Here is the chlorochromate reagent. It is negatively charged, and the counter ion is the conjugate acid of pyridine. That's where the pyridinium comes from. The interesting thing about pyridinium chlorochromate is it's soluble in organic solvent, and that will become important to us a little bit later. All right. So the first step in this reaction is going to be oxygen attacks the chromium. The chromium is very electron poor. It's chromium 6. And though we're not worrying about the orbitals, it should seem reasonable that we're going to attack the chromium here and replace an oxygen chromium pi bond with an oxygen chromium sigma bond. And that should be downhill in energy for familiar reasons. Oh dear, I've done something that your text doesn't do, so I need to revise. I need to revise what I was going to show you. We're going to think of this, even though what I was showing you is fine, we're going to think of this, and it's simpler to think of this as an SN2 reaction. That is, we replace a chromium chlorine bond with an oxygen chromium bond. So that's just sort of an SN2 style reaction. At this stage, your text shows you something that I will show you here, though it's not necessarily that interesting. You remove a proton from the protonated oxygen, and then the negatively charged oxygen on chromium picks up the proton that you just removed from some other source to give you a neutral intermediate. Now, every year I get people asking, first, why do we have to do this? Frankly, I'm not sure. I don't know what the empirical evidence is for these two things happening. Though it stands to reason, since positively charged oxygen with a proton on it is acidic, it stands to reason that some base could remove that proton. Why do we have to protonate the negatively charged oxygen? I'm not actually sure we do, but your text tends to show that. And in fact, some people ask, why can't this oxygen just reach over and pull the proton off directly? I think that might be reasonable. However, the bond angles are not conducive for this oxygen to attack the proton from behind. So it's a little bit dicey as to whether or not that could occur. In a lot of cases, your book will just do this and say 2 proton transfer steps. Okay, so that's not an important part of the mechanism that I'm going to ask you about. But when we look at this neutral intermediate, one of the interesting things that you can see is if you define this part of the molecule as a decent leaving group, then the oxygen is at the alpha position and the carbon is at the beta position. You now have a proton that is beta to the good leaving group. And so you can do the type of elimination reaction we've been doing for a couple of weeks now. You could have some base, and it doesn't need to be a strong base. You don't need to add it. Your text will probably show you that it's Cl- doing the proton removing. I don't care what it is. You remove that proton, you create a new carbon-oxygen pi bond, and the leaving group leaves. In so doing, you now make a new aldehyde, and chromium leaves with 2 electrons that it owns directly now. So if you're counting oxidation state, this should be chromium, I think 4 now instead of 6. I could be wrong. I'm not actually even sure, but it should be that. All right. Questions so far? Okay, so that's oxidation of an alcohol to an aldehyde. This is a primary alcohol, and I'll just summarize the reaction here. PCC takes the alcohol to the aldehyde. Now, what about a secondary alcohol? What would you expect that to give you? You get to that intermediate, you remove the proton, leaving group leaves, and that gives you the ketone as your product. Primary alcohols become aldehydes, secondary alcohols become ketones. Now here's a fun question. What about tertiary alcohols? Let's sort of examine what would happen if we did the first few steps. What's my problem here? I've been trying to figure that out my whole life. What's my problem? There's no beta proton, right? So that you can't do the elimination reaction, you can't oxidize any further. So are there other side things that could happen? Possibly, none that I'm worried about. We'll just say no good. No oxidation. Okay, so strategically, if you're planning a synthesis, don't ever try to oxidize a tertiary alcohol. It just won't work. Now again, is it a good question on an exam for me to say, here's a tertiary alcohol, here's PCC, what do you get as the product? I mean, I suppose, but now you know, so again, that just tests whether you can look stuff up, not whether you understand. I might ask you, why doesn't the reaction of PCC with the tertiary alcohol work, and you could explain that. All right. What else? Yeah, go ahead.
It's just to confirm, but we wouldn't expect the lone pair on the oxygen in the middle to attack the positive charge on the other one, the bond, because there.
I'm sorry. Sorry. Really slow. Oh. Yeah, I mean, you could imagine this happening. It's just that removing protons is like it's an SN2 type reaction. It happens via backside attack. And the question is, can that oxygen get to the backside of the proton? And so I happen to know, based on some other studies in organic chemistry, that in a 4-membered ring, that's a tall ask. But I don't think it's unreasonable enough that I'd mark it wrong if you just showed something like that happening. Yeah. So what forms a double bond in the last step of the primary alcohol? It's that in the primary alcohol, you do have a proton that is beta to the leaving group. Same thing with the secondary alcohol, but in the tertiary alcohol, no, it doesn't happen. Okay. So what forms for the tertiary alcohol? Again, I don't know. It's possible you could do, well, I won't even worry about it because I don't expect you to know that. So one question we're going to deal with next time is, what if we wanted, instead of just going to the aldehyde, what if we wanted to take the primary alcohol and go all the way, not just to the aldehyde, but the carboxylic acid. On our original diagram, that would have been going up 2 floors, from alcohol, 2nd floor, up to the 4th floor directly, instead of just stopping at the 3rd floor. And it turns out there is a way to do this, but I'm going to wait until next time to tell it to you. Dun, dun, dun. So, see you Wednesday.